Hey guys, we're inching our way closer and closer to the AP Calculus exam. We're working through all of those old free response questions that have been released. We're in 2017 looking at question number 1. It is calculator active, and it's a great question for both AB and BC students. So we've got a really nice tabular question here today, and I would say 90% of the time that's going to lead us into, approximating an integral using some type of Riemann sum or trapezoidal sum and some other approximations that we'll make based off of this table. So right out of the gates, they're describing a tank that's 10 feet tall. So let's imagine that our tank right here has a height of 10. Now, what's in this table are the areas of different horizontal cross sections, and that can be sometimes hard to visualize. So they're saying when h is 0, okay, we're 0 feet above the ground, this really thin slice, basically the surface area of that bottom is 50.3. Now, as you go up, if you go up 2 feet, if you go up 2 feet higher and you cut out a thin slice, now that cross-sectional area is 14.4. So this picture that I imported is not a great picture because my picture has a uniform radius as you go up, and you'd expect the area of all the cross sections to be the same. So maybe picture like a vase or something where as you go up, the cross sectional areas change and wave a little bit. And so anyway, the cross sectional areas are measured in square feet. A is continuous, which is great to know, and he also decreases. That's really good to know. Okay, so we jump into part A, and they said use a left Riemann sum with 3 subintervals indicated by the table to approximate the volume of the tank. Now, there's actually nothing in that question that says I need to be integrating, although you'd probably connect the dots. As soon as they said left Riemann sum, you're probably thinking I'm going to approximate an integral, so that's really good. Now, exactly, I guess the question is, that's lying beneath the surface, why am I integrating, right? Well, here's something that's really valuable that you probably pick up in other questions. A lot of times when you do the area volume questions, one of the questions has to deal with the volume of some object with known cross sections. And as we work through that process, we're really integrating the cross-sectional area of whatever those known cross-sections might be, whether they're semicircles or squares or rectangles. So at the end of the day, kind of stick this in your back pocket. If you want to find the volume, all you have to do is integrate the cross-sectional area, okay? And so in this particular case, those bounds are going to be from 0 to 10, and this integral is approximately, let's see, the first rectangle has a width of 2, and we're going to use the height at a of 0, which is 50.3. And then the distance between a 2 and a 5 makes a base of 3. We're going to use the height at h equals 2, so we're using 14.4. And then that third rectangle, as we go from 5 to 10, has a width of 5, and we'll use the height at 5, so we'll go 6.5. And again, it's calculator active, so we'll throw those into our calculator. We got about 176.3. That's going to be cubic feet. So we just approximated the integral to be 176.3 cubic feet. And they want to know, is this an overestimate or is this an underestimate with regards to the actual real volume of that tank? Well, notice that little hidden secret up there in the beginning of the problem that said h was a decreasing function. Strictly decreasing. I mean, the table certainly implied that it was decreasing. I think it started at like 50.3 and went down, down, down. So A is continuous. They said he's strictly decreasing. So now if you were to go and draw a left-handed rectangle anywhere in here, I just picked 2 random points on the x-axis. Okay, here's the left endpoint. We go across, boom, boom, boom. You notice how we overshoot the curve just a little bit. So we have created an overestimate. Because why? Because the function a of h is decreasing. That's the magic word. You definitely want to mention that a of h is decreasing. All right, let's see what C's got hiding in there for us. So they said, okay, now consider the area of those horizontal cross sections to be modeled by function f. So we're done with the table, and we're replacing it with this function f of h. Based on this model, find the volume of the tank. So now we're still integrating from 0 to 10. But now we're integrating the function f of h with respect to h. And again, this is just pumping it straight into the calculator. We're going to get about 101.325. We're carrying 3 decimals. Again, we're describing volume, so it's going to be cubic feet. And that's all there is to part C. That's all there is. And now here, finally, in D, this is the real tricky part in the question. I think if anything derails us and keeps us away from that perfect 9 out of 9, this is probably going to be the part that gets us. So now they're talking about, they said, hey, try to envision water being pumped into that tank. And when there's this instantaneous moment when the height gets up to 5 feet, they said at that particular moment, the height is increasing at a rate of 0.26 feet per minute. So I made a note to myself here that dH dt is going to be 0.26 feet per minute. And notice how I used, I did say dt. I'm already thinking that the derivatives with respect to time because they said per minute right there. All right, now, using that model from part C that was describing those cross-sectional areas and stuff, find the rate at which the volume is changing. So to find the rate at which the volume is changing, that's going to be what I like to call my dV dt. So I first need to create an expression for V that's in terms of H, and then derive that all with respect to time. And I think just writing V in terms of H is a skill in itself. So we're going to say the volume is going to be the integral from 0 to any random height. Now in that case, function f needs to be in terms of a different variable. So we'll just kind of use a temporary dummy variable as x, okay? And so this expression would measure the volume at any particular height. And of course, we want to derive it with respect to t. So we'll say dV dt equals. Now, I'm going to do a couple of things. Notice how this one's with respect to h. Or rather, I should say, just remind yourself that we're deriving with respect to t. So we're going to use that second fundamental theorem. And the first phase says substitute this h in for this x. So you're going to get f of h. But remember, you're not done. We now have to multiply that by the derivative of this variable right here. Now, if I was deriving with respect to h, I'd say the derivative of h is just 1. But because it's with respect to t, I'm going to say dH dt. So we're using the second fundamental theorem with, kind of think of it as a chain rule, so to speak. So now we could say, all right, dV dt at the moment where h equals 5 is going to be f of 5, which I can use my calculator to evaluate, multiplied by 0.26 as the given value. And we're just going to pump all of that into the calculator here. And let's see what my calculator says about 1.694. Now the units are going to be, think about how you measure V, that's going to be cubic feet. Think about how you measure T, that's going to be in minutes. And that's all you got to do for your units. So there's a beautiful final answer. So I bet you absolutely crushed A, B, and C. And I hope this version of D makes a little bit of sense and it's something that you can take with you and put in your toolbox going forward. All right, have a great night.